Hey, it's Mrs. Weethy, and I'm back for Unit 6 video lesson number 9 on the nature of solids. So the key question here is, how are the structure and properties of solids related? Well, we have studied solids before, and we know that the general properties of solids are related to the arrangement of their particles within a substance. So how are their particles arranged? Well, in most solids, the atoms, ions, or molecules are tightly packed together so that the solids are very dense and not easily compressible. So if you look at the diagram here, you see all of the particles are very closely packed together. And so there's not much volume in between the particles to squeeze them closer together or to compress them. So they're not very compressible. So what about the motion of the particles in a solid? Because according to the kinetic molecular theory, we know that all particles are in constant motion. Well, in solids, the particles tend to vibrate about the fixed points, thus the solids do not flow. So where all of these particles are fixed into their position, they're kind of going to vibrate back and forth within that solid structure. What happens when a solid is actually heated? When we heat the solid, so take a look at this, and we see these X's and these little semicircle kind of doodad things represent the whooshies. And so we see when it's cold, the particles are vibrating, but when you heat them up, they're going to, the heat from, or the energy from the heat is going to be transferred to the particles, increasing their kinetic energy. So those particles are going to vibrate more quickly with more energy, until it reaches a certain temperature, and then at that certain temperature, the disruptive vibrations of the particles, they're essentially going to vibrate so much that those vibrations are going to be strong enough to overcome the attractions that hold them into their fixed positions, as we see some of these particles are being ejected from the surface of that solid structure. The freezing point then is the temperature at which a liquid changes into a solid, and the melting and freezing points of a substance are actually the same temperature. So at that freezing and melting point where you go between the liquid and the solid phases, at that particular temperature, then the liquid and solid phases are actually in a dynamic equilibrium. So we see that some of these particles, when it reaches that temperature, those disruptive vibrations are going to absorb enough kinetic energy that those particles are going to go into the liquid phase. And then as these particles in the liquid phase are moving around and bumping off of each other, may collide back into the surface of the solid and then go back into the solid state. So we have particles going back and forth into the solid and the liquid states, and therefore you have a dynamic equilibrium. Ionic solids have a high melting point because there are relatively strong forces that hold them together. So what kind of forces do hold them together? Well, when we're talking about ions or ionic solids, you have the positive and you have the negative ions. And so it's simply those positive, very strong positive and negative charges that are holding those ions together in the crystalline structure. And if we take a look at this, sodium chloride has a melting point of 801 degrees Celsius. That's extremely high. On the other hand, molecular solids have low melting points. And why is that? So water in the solid phase as ice has a melting point of 0 degrees, which is much lower than we see that of sodium chloride. So if we take a look at this, here you have a water molecule, and here we have a water molecule, and it's the intermolecular forces, the hydrogen bonding, although the strongest of the intermolecular forces, is still much weaker than an intramolecular force. So it doesn't take as much energy to break these attractions between the water molecules as it does to break these attractions between the positive and the negative ions. So what makes up a solid we have crystalline structures. The particles are arranged in orderly repeating three-dimensional patterns, which we call a crystal lattice. And we learned this a little bit earlier in the school year. The shape of the crystal reflects the arrangement of the particles within the solid. So we see the chlorine and the sodium ions, and their natural arrangement just gives them a cuboidal shape. So they naturally come into these shapes. Crystals are classified into 7 groups, which we call crystal systems. And if we take a look, now you don't have to know all 7 of these, but given a structure, just to know that the sides are labeled, the edges are labeled A, B, and C, and the angles are labeled alpha, beta, and gamma. The 7 crystal systems differ in the terms of their angles between the faces and in the number of edges of equal length. And again, like I said, these are the 7 different crystal systems, but you don't have to know exactly what they are, just to know that they exist. The shape of a crystal depends on the arrangement of the particles that they have within it. The smallest group of particles that keeps the geometrical shape of the crystal is known as the unit cell. Within a crystal lattice, you have a repeating array of any one of 14 kinds of unit cells. That's in a crystal lattice. In a crystal system, can be composed of from 1 to 4 types of unit cells. And let's take a look at that. So here we have 3 kinds of unit cells that can make up a cubic crystal system. So cubic, the cuboidal shape, is a crystal system, and it has 3 kinds of unit cells. We have a simple cubic, which is just, you have atoms or ions that are arranged at the different corners. In an imaginary cube, you have what is body-centered, and in a body-centered, you have atoms or ions, at the corners of the imaginary cube, with one in the center. And then face-centered basically is like where you have a cube within a cube. And these are the 3 actually that I want you to know. Now, we have what is also called an allotrope. Some substances, elements in particular, can exist in more than one form, and we call those allotropes. So if we take a look at carbon, carbon has 3 common allotropes. You have the diamond, and in the diamond, you have the carbon atoms that are bonded to 4 others in a very, very tight, rigid, compact structure. In graphite is a little bit more loose, but it has hexagonal arrays that are basically layered on top of one another. And then you have another one, which actually was discovered not too long ago. The Buckminster fullerene, which is made up of 60 carbon atoms, forms a hollow sphere, and the carbon atoms are arranged in pentagons, so you can kind of see a pentagon right here, and also hexagons. Now, I just read an interesting article recently that these fullerene hollow tubes are being used as delivery systems in some of the newer medicines, drugs that are being developed. Now, the physical properties of diamond, graphite, and fullerenes are different because of their structures. Diamond has a high density and is very hard. Graphite is fairly low density and is very soft, as you guys know, because when you're writing with a pencil made up of graphite, it can break very easily. And the hollow cages in the fullerenes give them strength and rigidity, but they're very, very small, so that they're actually able to travel through plasma membranes. That's how they're able to use to deliver medicines across the plasma membranes. Allotropes are 2 or more different molecular forms of the same element in the same physical state, but they have different properties. In addition to carbon, phosphorus, sulfur, oxygen, boron, and antimony all form allotropes. So what is a non-crystalline solid? You can have solids that don't really take on a crystalline shape. These are called amorphous solids. And in an amorphous, now here's the structure of a crystalline solid, and you can see it's pretty orderly. In an amorphous solid, however, it really doesn't have an ordered internal structure. So things like rubber, plastic, asphalt, those are all different kinds of amorphous solids. Another kind of amorphous solid also is glasses. So a glass is transparent fusion product of inorganic substances that have cooled into a rigid state without crystallizing. Sometimes they're called supercooled liquids, but nonetheless they have irregular internal structures, kind of somewhere in between those of a crystalline solid and those of a free-flowing solid. So that ends this video lesson. And I'm going to leave you with my sign off, where I want you to be happy, have fun, and just dance. This is Mrs. Weethy, so long for now.